好，好，各位好。那这一场是那个叶家俊带来的那个跟Backend Optimization 有关的。好，那我们欢迎他，谢谢。
Hello, hi. Um, Good afternoon. I'd like to thank everyone for coming for this session that I want to design in a way that both locals and foreigners can understand. So I will speak more slowly. But if you don't understand, you can look at the slides to understand what I'm expressing. If we run out of time, I might speak faster. Okay. Today I'm here to discuss my experience with Postgres. If you're a backend engineer or a database administrator, I hope this presentation will help you improve your project. Even if you are not, this may inspire you to discover more interesting features of Postgres. We've actively used Postgres features in our backend project. These features provide significant performance improvements. They make our API endpoints faster and more stable. By the time we finish, you know how to apply these features to your own project. So let's dive into this topic. Before we get started, I want to mention that my former colleague accomplished the bulk of this work. I have rearranged the material to make it more suitable for formal presentation, so everyone can understand it more easily. He's also here as a co-speaker, so if you have any questions, you can ask him too. Let me introduce myself briefly. My name is Ye Jiajun. I have 6 years of experience in backend development. My favorite technologies are Golang, Postgres, and Kubernetes. Recently, I've been focusing on backend development, especially in financial trading. I was a CTO and VP of a startup, and before that, I was a backend developer. I'm currently open to work, so if you have any job opening, please feel free to reach out. For more information, such as my resume or LinkedIn profile, you can visit my personal website via the link below. You can also access this presentation there. You need to access these slides, just type in xnum.in in your browser and navigate to explore my talk button. You will find it. I've divided the presentation into the following parts. We will start by discussing the background of this project, covering its development and challenges. Next, we will outline our objectives for improvement, particularly focusing on addressing issues from the initial implementation. After that, the most important part is to introduce the Postgres features we utilized, such as materialized views, CTEs, generate series, and more. Finally, I will wrap up by summarizing the benefits and key takeaways from this implementation. Let's begin with a look at the background of our project. We had a backend project with an API service. The primary goal was to provide user access to their profit and loss data and related analysis. This includes running totals, available fund amount, and grouping by various criteria, such as fund, account, and user. We also aim to support multiple timeframes, including daily, monthly, and yearly records. This project was under heavy development, dealing with frequently changing requirements. So we implemented in the application layer, prioritizing accuracy over speed. We implemented the first version quickly, and everything looked good at first. However, after a while, we encountered the first challenge. The speed of API responses started to slow down. After some investigation, we found that the slowdown was due to the frequent database communication. To address this issue, we started considering building a cache layer to reduce this communication. And the cache layer was built within the application. As we already know, in computer science, cache is often referred to as the devil of everything. Let me explain why. First, warming up data took about 1 minute. This caused the API startup to slow down, although it was mitigated with rolling updates. However, it still poses some issues. If you needed to restart a service or start a development environment, it would take additional time. Additionally, each process consumed nearly 2 gigabytes of memory to store cache data. Even though it wasn't a perfect solution, it mitigated the problem for about half a year. When the system stabilized and no one wanted to add new features, we thought it was time to improve it. We started considering moving this feature to the database layer. This could reduce data communication because the cache will be handled by the database. Now that we have an understanding of the background, let's turn our attention to the objectives we want to accomplish. First, we needed to ensure backward compatibility to prevent the loss of any features from the first version. Second, we aimed to simplify data retrieval by using a single SQL query. This can eliminate the need for any computations within the API service. If the table schema design is not well optimized, it could lead to full table scan, which can be very slow. We decided to make some trade-offs by providing more storage space in exchange for faster query execution times. We estimated the disk space required. Considering raw data amounts to millions of records, we believe it wouldn't consume too much disk space, possibly some gigabytes, and definitely less than 1 terabyte. Unlike processing huge data set, our data set is smaller, and the disk space is affordable, so storage duration is not a concern for us. In order to achieve our goals, we designed an essential table with the following columns. The first 5 columns are used as indexes. These columns always appear in SQL query conditions, and having an index on them can reduce the time needed to look up data. The last 3 columns stores users' profit, the task they paid, and their available amount. These are the results we usually need to know. We expected this table to allow us to perform the SQL queries listed below. For instance, if we want to query the daily records for user ID 1 and only want the last 14 days, we can execute a simple SQL query. Similarly, we can retrieve monthly records for the last 12 months, or all yearly records in the same way. This approach eliminates the need to write complex queries. All the hard work is handled by the implementation of this table. Next, let's dive straight into the key features we used. Some of these may be a bit difficult to understand within a single slide, but you can write down the keywords and find some tutorials later. The first feature is the materialized view, also known as M view. What's the difference between an M view and a standard view? When we query data from a standard view, it runs the viewer's query and generates a temporary table, then returns data from the temporary table. But end views store this temporary table physically. You have to manually trigger updates, so it could be inconsistent with the actual data. However, this trade-off eliminates the need to execute a complex SQL query repeatedly. End views are a good fit if your views takes a long time to return results and you don't need to maintain up-to-date accuracy. They are ideal for use cases such as data analysis or generating reports. The next feature is Common Table Expression, CTE. It allows you to write SQL queries in a more modular and readable way. CTEs enable users to define one or more temporary result sets for use in subsequent queries. For example, first, we define a temporary result set called total sales. This set provides the total sales amount for each employee. Then, we can use the total sales table to find out which sales make more than 700 in income. If you use a subquery, you can achieve the same result, but the SQL query would be more complicated. Sometimes, if you need the subquery within another subquery, it could be hard to read. So, we often use CTEs to make SQL queries more modular and easier to understand. The next feature is Generate a Series. It's a function that generates a series of values. In our case, we only need to show the trading date. A trading day is a date when the exchange is open for trading. Generally, it includes weekends, holidays, and typhoon days. Therefore, we need a way to generate a list of trading dates. To identify trading dates, we use a holiday calendar table to mark weekends, holidays, and typhoon days. Notably, before 2019, there was a unique phenomenon in Taiwan stock market where the exchange might open on Saturdays due to make-up days. Sometimes the government moves a workday from a weekday to a weekend, causing a shift where you have to work on Saturday. To sum up, if a date doesn't appear in the holiday table, it must be a trading date. Here's a demonstration of the generate series function. We generate dates from April 1st to April 7th with a one-day interval. The result looks like the example shown on this table. This is a complete example of how to find the trading dates. First, we have a holiday table and then we insert some data to demonstrate its usage. Next, we use a CTE to generate the trading dates. In this example, we have a constant range for the beginning and end dates. But in a real system, the beginning date is when the system went into production, and the end date is the current date. The query result looks like the example shown on the right side of this slide. You can see the New Year's Day is filled out. By using this CTE and the holiday table, we perform a left join to find which days do not appear in the holiday table. The next feature is lateral join. You may be familiar with subqueries, but perhaps not with lateral join or window functions. Lateral join has similar functionality to subqueries, but it has its own advantage and limitations compared to others. In some cases, using lateral join instead of a subquery can lead to better performance. If you encounter performance issues, you might want to consider exploring lateral join or window functions. Sometimes they may help improve performance. Let's take a look at this example. First, we create a table called fund histories. It's a sparse table, so it only keeps records of the dates when user funds changed and the amounts of those exchanges. And then I'd like to know the amount the user obtains for each day. First, I generate a data series that represents the data range I'm interested in. From the previous slide, we know that the table only keeps 2 records, which are changed on April 1st and April 5th. By using a lateral join, we can find the records in fund histories and derive the obtained amount for each day. Next, I will introduce window functions. Window functions are definitely powerful tools for performing calculations. You will probably use them before, such as sum or count. But the window functions also provide many other calculation functions, such as running totals, moving averages, and ranking. We will use the window functions to calculate the total profit as a running total from profit records. Let's start with some random data. For example, a sales table with columns for ID, store ID, sales date, and profit. This table shows the profit earned by each store every day. So, a basic usage would look like this. The total profit is an accumulation since the first date, and we want to have a summary for each store and every date. We can partition by store ID and order by sales date. You can see that the total profit is the accumulation of profits. For example, for store ID 1, the total profit on April 2nd is 100 plus 150. So the total profit is 250. Now we have a daily profit table that looks like this. However, it lacks monthly and yearly records. To generate these, we first need to create 2 virtual columns called deal month and deal year. If we have a column with a data type of date time, we can use the toChar function to generate a new column. This column can extract the necessary information from the date time column and then produce a new column. So now we can extract the month and the year from the date. It can be utilized during table creation with a generated column feature. Or if you don't want to create a new table, you can use the CTE to achieve the same results as shown in this example. Next is group by. It's a very commonly used feature. With group by, we can compute monthly and yearly records by aggregating daily records. The result is shown on this slide. Given that we have daily records on the left, these are raw data. By using group by, we can sum all days in a month for each store. This produces a monthly sales data. So now everything is ready. We need to merge all the results into a single table. The union clause allows us to merge multiple result sets. This way we can combine daily records, monthly records, and the yearly records into a comprehensive summary. To sum up our discussion today, I'd like to share my takeaways. As backend engineers, we've delved into advanced database features, significantly enhanced backend performance. Additionally, the table allows for direct data access and report generation from database. However, this comes with some downsides. For example, It takes about 60 seconds to refresh the materialized view, but since it refreshes in the background, the efficiency gain is worthwhile. Previously, we stored data in the API service. If we needed to query data for one-time use, we have to find a developer to create a one-time API for that requirement. Now we can use a database GUI or a simple Python script to get the result. This reduces development costs and maintenance issues. The only downside is the rapid increase in SSD wear. We addressed this issue by investing in enterprise SSDs, which offers a high write endurance of 15.2 petabytes written. I believe these SSDs will last for at least 3 years, even under heavy usage. Lastly, if you don't mind, there will be a time for a Q&A session at the end. Feel free to ask about any part of this presentation or share your own experiences with SQL optimization. I have to let my co-speaker hold this section because my next presentation will be starting at 1:30. Thanks for your attention. 然后他不会讲英文，所以你们可以用中文问他就好。
有啊。
嗨，请说。
你好，我想请问一下，那像你们这些就是运用这些 query 整理出来的，比如说语句，会用 SP 的方式去抠吗？还是说会是怎么样的方式去进行呼叫？
就是这些是直接 create 在 data， 就是直接下 row SQL 去 create 这张 mView， 然后我们的 backend 是 Golang， 所以是直接用 GORM 这个 ORM 的 package 来直接就是直接用 ORM 来查询这张 mView 这样子。
所以就是
你说的是 SP 吗 ？SP 可以帮我是什么
store procedure。
好，这个我可能就不太确定，就是没有这方面的策略这样子。
所以就是先把 materialized view 整理好，然后用 ORM 去抠。
对。因为这个追根溯源，就是因为程式有点难维护了，然后 cache 起来也不太有，就是价值不高，所以就打算直接就是测试写好之后，直接把这整个计算丢给 DB 做。
所以就是把原本 API 需要扣的资料，想办法整理成可以直接拿的 MV 表。
对。
然后程式端就直接
程式端就直接把程式码全部砍掉了。
了解。那个 MV 表它的 refresh time 你们是怎么设
？refresh time 我们是设2分钟一次，然后一次大概是要执行60秒，所以会有就是它的脏资料的时间大概最多会是2分，会是1分钟这样子。
就是维持大概1分钟的新鲜度。
对。但是因为我们的资料即时性，这个是没有这么急迫的资料即时性，因为在 API 层还是会用 WebSocket 去跟 Client 去直接给，比方说报价或其他资讯，去让前端来组即时的损益，所以资料持久层的部分就可以用 mView 来解决。
那这样对 DB 的 performance 或是一些效能会造成什么影响吗？
当然一定是 DB 的 loading 会变高，但是我们就是这还是有很多可以最佳化的空间。最一开始会有这个决定，是因为 API 层的计算量，真的太大了。就是一个 query 进来可能要，最久会到3秒才给 response， 这不太可以被接受。
了解，谢谢。
还有其他？
你好，因为简报有提到用那个 CTE 来做 query 的优化，那我是想问说，在 CTE 那边， 会遇到你的 query plan 的问题，不知道你这边有没有遇过？因为像在 PG12以前的版本 CT 它的 query plan 的话是，第一次查询它就会是 materialize，所以它之后的 query plan 有可能会是不好的。那你们有怎么去处理过这种问题？
这个当初就是这整段流程，当初是在大概去年年初的时候，是我跟 我跟 ChatGPT 一来一回的时候去写的，然后很快兜出一个 POC，所以这个版本完成之后，大概半年内我就离职了，所以后续的优化我不太清楚，但是当初只是要先赶快把这个效能issue解决，就是没有太去细究说。它在第一个 query、第二个 query 就会被 materialize 这样子，
好 ，OK， 谢谢。
但是确实就是，如果就是 MView 搭配很多 CT 还是有很大的优化空间的。
好，谢谢。
想问一下，不知道你们在处理搜寻的时候有没有处理一些 auto complete 的情境？对
，auto complete
对，
哦，没有，就是这一整段单纯就是计算损益的部分。
了解了解。
还有问题吗？
你们刚刚有提到，就是你们是原本把在 Backend 的工作就移到 Database 做了，那原本是会花3秒钟的部分，就算移过去，应该也是会花3秒钟。
没有
你是说它的时间是到底是怎么省掉的？
时间怎么省掉的？其实就可以直接想象成是把 cache 的部分放在直接放在 DB， 然后因为原本是会先把，比方当时的架构就是我们会捞整个所有使用者的资料出来，然后再就是也没有做什么，也没有做批次或是 pagination 之类的，一次捞出来，然后在 DB 在程式算完之后，再可能 cache 在 Redis 里面，然后这一段经过很多人经手过，跟很多 feature 的浇筑之后，它已经变得很难维护了。然后你说你的问题是它到底省下多少时间？就是我们最后 query 的时间可以降到可能50毫秒以内，或是就是把所有计算时间丢给 refresh materialize view 的过程这样子。所以时间是因为当时的条件是因为我们公司的机房是地端的，对，所以没有什么 DB 的执行的成本，没有电费就当不用钱这样子，没有什么云端的成本，所以可以这样子，也不能说随便搞，就是可以把 loading 放在地端的 server 这样子。
我在猜会不会是因为后端把一大堆资料捞过来，然后那些传输的时间其实是占最多的。
对，就是 decode 和 encode 一定会有时间，
就可能不是计算的时间，而是把资料从 database 捞出来那些传输量。
ORM 的 payload 确实会有造成效能 issue。
OK， 好，谢谢。
还有。
可以。好，这个资料规模，首先，大概就是交易日，1年的交易日大概就是240天，假设，然后大概有400-500位 user， 然后每位 user 光他的资金，就是资金的记录，就是刚刚说的这个什么， 看一下。这个吧，哦，这个放置，那它就可能会，其实资料量并不大，然后 sales 的 record 大概是400-500万笔，对，所以实际上资料量并不大，但是放在程式里就会需要一直从第一天算到最后一天，再从第一天算到最后一天，所以后续的优化其实可以把某一年的算完之后 snapshot 起来，然后再就是我们只要算可能某一年度的，就是可能当年度的计算量使用这个方式，那其他的使用 snapshot 再 join 起来就好，就可以省下很多不必要的重复计算了。这个算是初版，对，就是 POC 的部分。请说。
刚才提到说你们会根据时间去算，那这边有考虑过 partition 吗？
你是说在程式里面 partition 还是
没有说 PG 里面的 partition。
当初没有这个想法，就是因为对，没有这个，当时没有这个想法。
哦，好 ，OK， 谢谢。
回去可以再研究，因为终究还是后端居多。
还有其他问题吗？好，那谢谢大家。
谢谢，耶。我先关这个吗？